Alexander Rössler. Let's have a round of applause for Alexander.
Good evening, ladies and gentlemen. Today I'm going to talk about Machinekit, machine control ready for the Internet of Things. My presentation will be in 4 parts. First, I'm going to tell you something about me. Then, I'm going to explain what Machinekit is. Furthermore, I'm going to talk about machine talk, the core topic of this presentation. And then we are going to show you a live demo of Machinekit in action. My name is Alexander Rössler. I'm currently studying embedded systems at the University of Applied Sciences Technikum Vienna. And I'm strongly involved in the open source community since now many years. And in the last few years, one of my main interests is 3D printing and application development and these things. So this was the how I found the way to the Machinekit project. And at the moment, as you can see here, I'm working at the Cool Tool on a new product. It's a 3D printer based on Machinekit. So, what is Machinekit? Machinekit started as a fork of the Linux CNC open source machine control project. We forked it in May of 2014, so last year. And the main focus of Linux CNC was and still is controlling CNC machines using desktop computers. So you see a problem here. Who of you still has a desktop computer in use? Only a few people. And who of you has a smartphone, a tablet? Okay, so we see new platforms have arrived, so there was need to change things. This was not possible in the Linux CNC project, so we had to fork it. The idea of Machinekit is to provide a framework for creating real-time applications and distributed setups. For example, the real-time environment can run on a desktop computer or an embedded system like a Raspberry Pi or BeagleBone, and it can be controlled by tablets, smartphones, or even the desktop computer as we see before. And it can be used for either the traditional use for CNC machines, or for the new upcoming 3D printers, or maybe for other applications such as robots or quadcopters, or whatever you may think of. And as you may have seen, there's a demand for communicating to each other. Linux CNC was designed to work on a single computer, but now we need to connect different devices with each other. For example, if you want to control a machine using a tablet, we need to connect to the real-time environment. And also we can think about different machines connecting to each other, or machines connecting to sensors on a network, and so on. And for this purpose, we needed to implement so-called middleware, which we named Machine Talk. And the main purpose is the interaction of non-real-time environment and the real-time environment. And furthermore, to support distributed setups. One of the parts of such a middleware is the transport. For this purpose, we use ZeroMQ, which is an open source end-to-end messaging library, which supports different communication patterns, such as publish, subscribe, and root the dealer. Yeah, you may know traditional applications are based on client and server, and with ZeroMQ we have the ability to do things like we already told you, publish, subscribe, where you have one provider who can send to many clients at the same time, and so on. And furthermore, a very important fact is that we have no startup order dependability, so a typical client can start before the server is up, and also automatic reconnect. Then for serialization is the process of converting application objects into wire format for sending them over the network. We use Google protocol buffers, which creates binary data and is highly optimized for different applications. The main advantage of using protobuf is that there is an implementation available called NanoBB, which is optimized for small embedded applications or even for real-time environments. So we can communicate from a non-real-time environment to the real-time environment without any proxy or something between. And as Machinekit is organized in services, we also may need a service discovery, because when we create configurations, we don't want to statically link, type in the IP addresses or so. And for this purpose, we use multicast DNS or DNS service discovery, which is also known under the name Bonjour or ZeroConf. And it works without any user interaction. It is decentralized, which means it's easy to extend, so you can create your own services without actually interfering with the software itself. So you can, for example, you can create a video service for streaming video data on the network without modifying Machinekit itself. It supports both multicast, which is good for automatic configuration, but however, multicast doesn't work in every network. For example, a VPN network doesn't support multicast normally, and the advantage of using DNSSD is that it also works with normal DNS responses, so it works also on in a unicast setup. And of course, we are living in the age of internet, so we need to talk to web browsers as well. For this purpose, an application exists that works as a bridge between machine talk and the web browser. In a web browser, we typically use JSON for serializing data, so we have a conversion between. Okay, we have a conversion between protobuf and JSON, and then we use WebSockets. So we need to convert between ZeroMQ and WebSockets. And yeah, this was basically machine talk. And now I will explain first how configurations are made in Machinekit, and then how machine talk is used. First, Machinekit has something called the hardware abstraction layer. You can think about it of something like a normal electronic circuit, where you have components, which can be either real-time or user-led components. Real-time components are typically created in C or C-like language called comp, and user-led components can be created in any high-level programming language, such as Python, for example. And also, there are many components available out of the box. For example, a PID loop is available, and other things like simple multiplications and so on. So you can use this hardware abstraction layer to create configurations without any programming skills. So you just need to configure the machine and you get a running real-time application. And yeah, of course we also have pins and signals to connect the components. And now you see this is mainly designed for a single computer running on a single machine. And we extended it using machine talk. We added the remote component. The remote component is something similar to a normal component, but however, it has an interface to the network. For example, imagine a button in a user interface. A button can usually be explained as something like a pin, and this pin toggles a signal in the real-time environment. As you see here, both pins on both user interfaces in this case are synchronized and directly interact with the real-time environment without any additional programming. So you just glue it together and then you have a running real-time application with a nice user interface. Furthermore, you have HAL groups. HAL groups can be used to distribute value updates of signals on a network. For example, think about a 3D printer or a CNC machine. These machines are usually Cartesian machines, so they use X, epsilon and Z axis. And we may want to know where they are in this Cartesian system. So we can use this to distribute the positions over the network. Furthermore, we have named ring buffers. This is a bit more complicated. In a real-time environment, things happen in real time, but however, on a non-real-time environment, you also may want to get data in the real-time environment and from the real-time environment in a sequential order. And for this purpose, this ring buffers exist. So you can send multiple commands into the real-time environment, preserving the order, and also get data out of the real-time environment. For example, an application would be an oscilloscope, where you may want to get value changes. These value changes usually happen very quickly, but in a non-real-time environment, for example, user interface is not that performant to show this value update in real time, so it pulls the values from this buffer. And another application could be to send commands to a real-time component from a user thread. For example, on a CNC machine you have G-code, and with the G-code you execute a few commands where you say, for example, you move to position 10, 10, and this command could be sent using such a ring buffer. So, now everything is said about machine talk, and it's we're ready to show you an example of Machinekit in action. This is our example setup. We have a small user interface running on this computer and also on an Android tablet. And we have a small setup consisting of a servo motor, an encoder, and a pit loop to control the motor, and also two differential components for displaying velocity and acceleration. Okay, we see here now the client application written in Qt Quick VCP. It's only one of the implementations. There are also applications available written in GTK or a web browser user interface using the WebDoc interface. So in this client application, you see I'm using the unicast approach, but it's also, sorry. I'm using unicast, but also we can use multicast if the network supports multicast, which it does not in this case. We connect, we get a list of available applications, but we also can use a local application to serve to display services. And we see here we have the motor control demo service, which provides the user interface. The user interface is not located on this computer, it's located on the beagable black we have here. So when we connect with a client application, the user interface is distributed over the network. And we have also a video service, which is an extension to Machinekit, which will display the motor and the wheel. So when I now connect, the application is distributed over the network, so we have a small timeout. Now the network services are connected, and we see here the demo application. We have here a few small user interface controls for controlling the setup. Here, display to show the current position, a button to turn the motor on and off, and here we can control the motor position. And we see here the motor is controlled by a pit loop. And when we play around with the pit controller settings, you see it gets unstable. And when we correct the settings, we get a stable system again. And here the video component just shows the wheel.
I'm moving it now from a second.
There is also the Android interface, which we cannot see here, and which has exactly the same user interface as here. So when someone is using the Android interface, it's automatically synchronized with the tablet interface. And these user interfaces can be created just with a few clicks or a few lines of code. There are dials and whatever sliders and so available. And these sliders, for example, represent a pin in the configuration. In the configuration, this would be, for example, the position pin, and the position pin is, as we have seen in the presentation, connected to the pit loop, which controls the servo motor. Okay, that's it. I'm at the end of my presentation. I get back to the presentation. If you want to know more about Machinekit, you can visit machinekit.io or the Machinekit mailing list on Google Groups. Thank you for your attention, and if you have any questions...
Yeah, there are a few questions over there.
I hope you are not serious, want to show us the hell definitions, or at least the definitions of the services which you expose.
Yeah, we can also show you the hell definition if you want.
And I would be very interested in the few lines of code to create a graphical user interface.
Okay. The user interface I will show on my laptop. It is this one here. And you see, it consists of a main QML file, which is basically for testing it locally. So this is not necessary in a distributed setup. Then a description file, which tells the configuration server that this is a an application with a name and a description. And then we have the main application file, which is just a tab view. And we have two QML files, which QML is a declarative language in Qt, which can be used to create user interfaces. And we have here the control tab. It looks complicated when you take a first look at it, but it's basically 250 lines, and most of these lines are for aligning the sliders on the interface, so they look good both on Android and the desktop user interface. So you see, for example, we have this gauge here, which is basically this small component, and we have an additional helping, and using and we have here this help application window, and this window automatically searches for help services on the network. So a basic Hello World demo would be a help application window at just a pin, and I'm usually not using the graphic designer because I'm more a programmer guy, but maybe it will work too, if we're lucky. Yeah. Yes. It takes some time, but sooner or later we will see that we can also just drag and drop the controls together.
To introduce myself, I'm Michael Pavela, and I'm Alexander's onboard mechanic for the demo. I'll just show them a fragment of the real-time configuration. This whole demo did not take a single line of C. That's all done with stock components, both his user interface but also on the real-time side. I need to zoom this up a little bit. It's all on the GitHub, the actual configuration which is running here. The configuration consists of really two parts. So, the actual talking to the electronics and the logic of interaction. Let's look at, for a second, that's the hardware interaction part. That's a scripting language called help command, which loads components. That's the components which Alex referred to, which have a name and export pins. The one is a signal generator for H-bridge, which drives the motor. Then there's a support for the GPIO pins on the BeagleBone. There's a hardware AB encoder in the BeagleBone chip, which is supported by the third component, and the BeagleBone CPUs, the ARM Texas Instruments Citadas, actually have two, if you will, Arduinos on steroids on board. Those are called programmable real-time units. It's basically a 200 megahertz 68,000. There are two of them, and we use them for stepper generation and PWM. So that's the fourth driver, which is loaded here. And let's just for instance, a part of the configuration of the quadrature encoder is the relation of the number of counts of the encoder for one turn of the axis to revolutions. Now that is a geared motor. It has about 45 revolutions per motor axis revolution for one axis revolution, and it has 64 AB signals per revolution on the motor. So we need to scale the position by about 3,000 to get from pulses to revolutions. That's the kind of configuration where you set pin values or set configuration values, and where you link things together. For instance, the position input output of the quadrature encoder goes into what's called the feedback signal, and I'll skip forward to the PID component because that's logically more interesting than the hardware wiring. That is where the PID component is loaded. We just need one. A typical machine might need 5, 10 maybe. We have the differentiators which do the acceleration and velocity estimation. We have the pro forma component which taps into the real-time part but really runs on the user interface. We call these the remote components. That's the definition, which starts with new comp and has a couple of pins which corresponds to the user interface elements which are demonstrated. We have the wiring of the PID components, the proportional, integral, and differential gain. And we could actually go through the circuit diagram, and you would find that one line corresponds to one wire in the circuit diagram. That's pretty much it. That's the setup, if you will. And the third part is how the whole thing gets into action. That's by threaded execution. Threaded means, in that context, means cyclic threads that runs with a servo rate of 1 kilohertz, can go up to maybe 5 or so on floating point threads. You take the functions of each of the components and thread them onto a thread in turn, and then you start the execution. So that's how the periodic execution of that component system works. So it's everything which is on that demo is driven by these scripts. There was no C programming involved. That's it.
Thanks a lot, Alexander and Michael. I think that our time is up for the second talk. I suggest we make a break of 10 minutes. But before we go on break, I would like to draw your attention to the money box over there.